Hello, today our group is gonna present the paper Selective Kernel Networks from CVPR 2019. The keywords of this paper are adaptively receptive field and split, fuse, and select mechanism. Here we go to the first section, paper introduction. The basic idea of the paper is how to construct a dynamic section mechanism to adaptively adjust the receptive field in CNNs according to the input. The author proposes the selective kernel convolution, which is a three-phase mechanism: split, fuse, and select. First, the input feature map is split into several different branches to do the group convolution. Two branches in the diagram for simplicity. You can see each channel has distinct convolution kernel sets. 3 by 3 in the first branch, 5 by 5 in the second. After the split, the information from all branches is aggregated by the summation operation. Then, the global average pooling layer embeds the global information into the vector of channel by 1 dimension. Further, it is followed by a fully connect layer. This part is a little confusing. You should notice that it is a softmax attention rather than self-attention. In other words, it is a channel-wise operation. The summation of elements in corresponding channels is 1. And the attention vectors A and B are derived by multiply Z by two learned matrix, upper class A and upper class B. The third phrase is selecting. We multiply result from first branch U1 with its corresponding attention weight A, and we multiply U2 by B and sum up them to get the final feature map V. This diagram illustrates the core part selective kernel convolution in the paper. And here we go to the second section. How do we re-implement the paper? We use PyTorch to do that, and because the SKNet is the improved version of ResNext, we refer to the official code of ResNext and replace all the group convolution with our re-implemented skconv. Therefore, our implementation can be divided into 3 parts: skconv, skunit, and SKNet. The pseudocode of skconv is consistent with the previous diagram, and the backbone of the whole whole SKNet is here. Each SKUnit contains 3 convolutional layers, and the middle layer is our skconv. Our third section is experiments and analysis. In order to test the effectiveness of SKNet and skconv, we test them on 2 datasets. First one is plant seedling from Kaggle, because we have not enough time and resources to perform experiment on ImageNet. We chose a small dataset to do 2 contrast experiments: SKNet 50 and its counterpart ResNext 50, as well as ShuffleNet plus SK and original ShuffleNet, which is a lightweight network. Notice that the only difference of the contrast experiments is whether the network uses skconv or not, and the result indicates that the networks with skconv are better on plant seedling datasets. These 2 experiments are consistent with paper. However, the experiment on CFAR10 seems unsatisfactory. The SKNet 29 with skconv is worse than the ResNext without skconv. After the double check of our code, we assure that all things including our experimental settings are consistent with the paper, except final performance. For the result, we analyze it and propose several reasons. First, we missed some details which are not illustrated in the paper. Second, the result is caused by some occasional factors. Third, maybe 29 layers is still relatively shallow, because as the network goes deeper and deeper, the receptive fields after convolution with different kernel sizes become more and more different. Therefore, maybe the efficiency of different kernel sizes is only obvious on deeper network.